Welcome to our discussion of the day. So we are talking about Ostwald process or the industrial manufacture of nitric acid. Now we said for you to form nitric acid, you need to do what? You start with the catalytic oxidation of ammonia. Okay, and when you talk about catalytic oxidation of ammonia, we simply say that ammonia is going to react with oxygen to form nitrogen 2 oxide, which is again further to be going to be oxidized to form nitrogen 4, which is going to be hydrolyzed to form now your nitric acid. So it means the last process in formation of your nitric acid is hydrolysis. Okay, so here in the absorption tower, it means this is where we are going to undergo hydrolysis because it is the last step. Now, another thing that you need to know under Ostwald process is during the formation of your acid, we say the ammonia undergoes catalytic oxidation, meaning we have, that is why you can see you have a catalytic chamber here, we have a catalyst here that is helping in the whole process of formation of your nitric acid, and our catalyst is which one? Platinum rhodium catalyst. That is the catalyst that we have there. Now let us begin. So we have the arrows, you can see the direction of the arrows, that is what is guiding us. So you have your gas A going to the purifier, and you have air. Now we said, so our gas A is going to be ammonia. Okay, our gas A is going to be ammonia, and we say we use dry ammonia, so it is pure dry ammonia. Okay, now our pure dry ammonia, we use pure and dry ammonia, and you can see here you have air being taken to the purifier. Why are we insisting on purifying our ammonia and using pure air? This is because we are using a catalyst here, and we are trying to prevent poisoning of our catalyst. So the air is being taken here to the purifier to prevent what? To prevent poisoning, of the catalyst. Okay, now you have your ammonia and your air being taken to the purifier, and then from the purifier the ammonia and air. So in the purifier you have what? The ammonia plus what? Plus air. Okay, now remember the important bit of this air that we are going to use is what? It is going to be oxygen, because ammonia is going to be oxidized. We've said catalytic oxidation of ammonia. That is the first step in formation of our nitric acid. Okay, so always keep that in mind. Now this pure air, we have now the air there, and we have the ammonia in our purifier. So from the purifier, we take the ammonia and air comes to the compressor. Now this is our ammonia and air, or ammonia and oxygen, but let us just talk about air. It goes to the compressor. What happens in the compressor? Now, the compressor is used to raise the pressure between the ammonia and your air for proper reaction. Okay, so here the compressor is used for doing what? It helps us to raise this is there. It helps to raise the pressure, or to increase, it increases the pressure between the two mixtures, the mixture between ammonia and our air. And from the compressor, our ammonia and air is taken to our heat exchanger. So heat exchanger, what happens here? The first thing that we are going to talk about is, remember we've said the active part of air that we are using in this case is oxygen. So this means your ammonia, this means that your ammonia reacts with oxygen here. That is what we've said, to form nitrogen 2 oxide plus what? Plus water. Now, if you're balancing the equation, we are going to balance by putting a 4 there, by putting a 5 there, and by putting a 4 there, and a 6 there. Now we have said that the mixture of ammonia and air is taken to the compressor, and this is to raise the pressure between the mixture, or to raise the pressure of the mixture, which is again taken to our heat exchanger. This heat exchanger is used to, the first thing that it does is cools down our nitrogen 2 oxide, okay? It cools down our nitrogen 2 oxide for it to be properly oxidized, okay, to form nitrogen 4 gas. And another reason as to why we are passing our mixture through the heat exchanger is to preheat the mixture. We are preheating the mixture for us to obtain suitable temperatures for both the ammonium and oxygen to react. So I have said the two things that we are doing here is to do what? To cool your nitrogen 2 oxide for further reaction, okay, for further reaction, which is the formation of nitrogen 4 oxide, because we are going to again react your nitrogen 2 with oxygen to form nitrogen 4. And another thing is to do what? To increase the temperature, between the mixture, to increase the temperature of the mixture of ammonia and air. Now, our ammonia and air is going to be again taken to the catalytic chamber. And in the catalytic chamber, now remember we have said ammonia and oxygen is going to react to form nitrogen 4 oxide, okay? And now the other part, or the ammonia and air, is taken to the catalytic chamber here. And we have said here we have the platinum. We have the platinum rhodium catalyst, okay? Now, this here in the catalytic chamber, we are going to oxidize, or this is where you have what? You have the oxidation. We say we have catalytic oxidation of ammonia. Meaning your ammonia is going to react with oxygen to form nitrogen 2 oxide, also here in the catalytic what? In your catalytic chamber. Now, we said we have the formation of nitrogen 2 oxide where? Here, because you still have the ammonia and oxygen. It is ammonia and air, so meaning we have oxygen in our air. So the ammonia and air, or ammonia and oxygen, reacted as we continue, as we go like this, ammonia and oxygen is reacting to form what? Nitrogen 2 oxide. So this arrow that is pointing to the reacting or the reaction chamber means that we have the nitrogen 2 oxide coming to the reaction chamber. Now what happens in our reaction chamber? In the reaction chamber, you're going to have oxidation of your nitrogen 2 oxide for you to form nitrogen 4 oxide. Okay, now let us write the reaction. So we have nitrogen 2 oxide reacting with oxygen to give you nitrogen 4 oxide. Now, how do we balance the equation? We are going to balance the equation by putting a 2 here and putting a 2 where? A 2 there. Now, we have our nitrogen 4 oxide gas that has been formed. So the nitrogen 4 oxide gas is going to be taken to our absorption tower. And we've said in the absorption tower, as you can see, you have hot air, meaning you have more what? More oxygen. Air, in the whole process, we are referring to what? Oxygen, because oxygen is the active part of air that we are going to use during this Ostwald process, other than what? Now the ammonia that we had there. So if you see hot air, just know it is oxygen. So you have nitrogen 4 oxide being taken to the absorption tower. And we said the last process in formation of your nitric acid is what? Hydrolysis. So here we have the process that is referred to as hydrolysis. Hydrolysis of what? Of our nitrogen 4 oxide. So the equation that is going to be here, it's going to be what? Let me write it here. So you're going to have your nitrogen 4 oxide hydrolyzed or reacting with water to form nitrous acid and nitric 5 acid. And how do you balance the equation? So you're going to balance the equation by putting a 2 there. So that is the whole Ostwald process. So something else that you need to remember about the whole Ostwald process is, one, that the whole Ostwald process leads to the formation of our nitric acid, which is 65% pure, okay? And another thing is that nitric acid is normally stored in dark containers. Why is it stored in dark containers? This is because if you expose your nitric acid to light, yeah, if you expose it to light, it is going to decompose to give you nitrogen, oxide, and oxygen. Okay, so we are saying if you expose your nitric acid to air, we are saying this is aqueous. Okay, so if you expose it to light, not to air, if you expose it to light, it is going to decompose to form nitrogen oxide. It is going to form nitrogen oxide plus oxygen plus water. Okay, so that is why it is stored in dark containers, and you're going to balance by putting a 4 there. Now that is it, a 4 there and a 4 there. So that is it about Ostwald process or industrial manufacture of nitric acid.